nanoconfined electrocatalysts. Why nanoconfinement, I would get to in a bit, but why electrocatalysis, I think we can all agree about electrocatalysis being at the heart of sustainable chemical and materials production, at least in the current era, as our world moves towards more intensely needed resources. It has been at the very center of a lot of processes that fuel our needs. Now, if you take a normal electrocatalytic system, there are typically three components. There is the surface at the very bottom, where a lot of charge transfer reactions occur. So this is what takes most of our attention because a lot of interfacial phenomena happen there. So a lot of aspects like the surface facets, surface defects, what kind of material you're using as an electrode play a role over here. And then the second bit is obviously the electrolyte or the blue fluid up on the top, which basically dictates the mass transport part of the phenomena. It essentially dictates how the chemicals at the bulk trickle all the way down until it reaches the interface and produce the reactions. And then finally, you have external applied parameters like the potential, the initial concentration, the temperature. All of these factors determine what kind of reactions occur and how fast they occur as well. So these are the three components, and we have our electrocatalytic system. So obviously, as researchers, we want our system to produce a really high reaction rate, a high yield, and we want the product high selectivity of the product that we desire, and we don't want side reaction. So these are outputs that we desire, and the way to go about it, most likely, is going to be trying to change one of the components of the system. And the component that's targeted more often than the others is the electrode or the material or the surface, because let's be real, it is the most visually present and the most easy element to change with respect to the entire system. So the way a researcher might go about changing the surface to enhance reaction rates could be maybe adding something onto the surface that enhances the rate of the reaction that you desire. So you add maybe adsorbed modifiers on the top, or perhaps you don't want a certain side reaction to occur. So then you poison the surface for it. So that's another way of adding something onto the surface. Some other techniques involve, instead of having a stable 1-1-1 surface exposed, you might go for a more active facet like 1-1-0 or 1-0-0. So that's where your surface modifications and defect engineering plays a role. And then the more, I think, obvious strategy out there is to nanostructure your catalyst because you're exposing a lot more surface area for the reaction, right? So these are all the different ways in which surface can be modified, and that is not what I'm going to be talking about today. I'm going to be talking about not modifying one of the components of the electrocatalytic system. Rather, I'm going to be talking about modifying all of the components in the system. How I do that is basically the second part of my research talk, which is nanoconfinement. What is nanoconfinement? As the name indicates, it's a way to confine or restrict the motion of chemical species at the interface. So you can imagine that, if the interface consists of pillars, you can move around, but maybe not as freely if, you didn't have any confinement. If you have parallel plates, there's only two directions in which you can move and not really as much in the third direction. In a pore, once you're in, well, you can only go through one direction, whereas if you're in a pocket, the way you go in has to be the way you go out. So with increased level of confinement, you have decreased degree of motion. Now you might think, well, if you're nano-confining something, you're restricting the motion of molecules in it. And we all know that for enhanced reaction rate, you want things to move as freely as possible because you want easy movement of stuff in, easy movement of stuff out. But here I'm restricting the motion. So how is this resulting in enhanced catalysis? Well, the way to think about it, I think, can be really simplified if you consider an example. Let's say you're a pretty busy person, which kind of all of us are, and you have been meaning to meet a friend that you haven't seen in a while. You want to perhaps say hi, grab some lunch, right? And you know she's going to be present in a really large lecture room. Think about 500 people in such a room, and you want to meet up with her. You can imagine how difficult it's going to be to spot her in that really large room and then move among all of those 500 people, walk up to her, say hi, and then grab lunch, right? Imagine if you didn't have such a large room and you had a smaller one, or maybe you were in an elevator and then she walks. It's going to be so much more easier to meet her, say hi, grab that lunch, right? So that is the essence of nanoconfinement. You're essentially enhancing possibility of interactions by restricting how much things can move. So you basically go from hello, anyone home to hi, nice to meet you. It's true for humans. It's true for chemical agents as well. It's just easy to meet the other component with which you need to react and then form a product. So more from a chemical perspective, let's consider a reaction. Green, which is the reactant, goes to a transition state, which is the blue star. And then finally, it goes to a thermodynamic product, or the golden yellow circle. Now, this reaction happens in a non-confined environment, which is this here. And it also happens in a confined environment where you have like the gray spheres confining the stuff. And there is the reaction energy landscape in both cases. In the first case, obviously, it's going to take a lot of energy to go from the reactant to the transition state. But you can imagine that if you confine with species that really stabilize this transition state, then you don't have to have such an uphill climb. It can be a little lower, because honestly, this one is a lot more stable than it was when it was not confined. In fact, in some reactions we have seen, this transition state is stabilized so much that it becomes a minima too, and it becomes a reaction intermediate. So the entire reaction landscape itself changes. So that's how you can see that reaction rate is enhanced. What about selectivity? Let's say you have a reaction and you get a bunch of sizes and a bunch of shapes. But you're only interested in a certain range of sizes, a range of shapes. You don't want the entire gamut of shapes and sizes. So you can see again how nanoconfinement can restrict the kind of output that you're getting and help you get more selective products. So nanoconfinement can enhance reaction rate as well as selectivity, the two areas that we want to enhance. Now, this is nanoconfinement. It can enhance reaction rate, but let's go a little deeper into some of the more fundamental effects that's going on as a result of the restriction. So we have mentioned before that, if you're restricting things, then things are going to collide into each other a lot more frequently and initiate the reaction, right? And that comes because of a lower mean free path length, right? So your kinetics, diffusion rates, all of those change under confinement. And then you have a changed electrical double layer profile also happening. So let's say if you have a charged surface, there's going to be an electrical double layer profile that's established. Let's say you put a confining layer onto the surface, which is lower than the Debye length. Then you're essentially perturbing the electrical double layer. And if you're perturbing it, that means that you're changing the equilibrium concentration of charged ions, which means you're opening up new ways of driving charged ions all the way into the interface via migration instead of diffusion, for example. So different ways in which thermodynamics is altered, and so is the kinetics. The third one is a little more simpler. It's pretty obvious, if you have a smaller enclosed space, large species cannot enter. So if your reactions involve solvated cations like lithium, for example, which is pretty large, perhaps it cannot enter. Then you can see that some of the reactions that require smaller components is more favored than the larger ones, right? So another way of impacting.
So lithium is large?
Solvated lithium.
Is the lithium is very small.
The lithium ion is pretty small, but when you have water dumped onto it, then it forms a really large hydration sphere.
So it becomes unstable in the.
So it's not able to enter the interface, right? But if you really have to like force it to enter, you have to spend some energy for it to shed
It's
it.
just unstable.
Mm, mm,
So
mm.
how big are we talking with these?
So confinement can be like of any length, but nanoconfinement has to be like within the nanoscales. And I'm currently working on a review paper, and we've realized that it has to be kind of like around 1.21, like less than 1.2, 1.3 nanometers, because water, so nanoconfined water forms like, bilayers, and only when your length scales is like around 1.2 nanometers. So like anything above that, water is not bilayer anymore. Water is multilayer, and multilayer water, at least the middle regions kind of behave like interfacial water anyway, so it's not special. But bilayer water like shows like really cool properties. So
Okay.
that's kind of the
So
length
we're
scale.
talking about like 1 or 2 rows of water molecules?
Yes,
Okay.
yes,
It's like
yes.
almost quasi like one-dimensional.
Yes,
but-
yes, very much so.
Three-dimensional.
Yeah. Very, very like small length scales over here. Any other questions? All right. And then the final effect, and this is the most popular one, the most dominant one, the most prevalent one, is just increased interactions. If you're an interfacial species and you're on the surface, you're either bonded to it or absorbed to it. Add another surface, you have double the chances of bonding, double the chances of adsorption, so you're a lot more stable. So that's what was going on in the previous slide, right? So these are some of the effects of nanoconfinement, but what I want to demonstrate in this slide is that it is not merely a one-dimensional effect like changing something on the surface. Adding a nanoconfinement like alters the very like fabric of how things move, how things react, what kind of species are available, the charge profile, like you name it. You're not changing the fish in your fish tank or the tank in your fish tank. You're changing the entire fish tank. So that is something I want to like draw your attention to before we proceed. Any questions so far? All right. So now that we have established,
Can you go, what does an electric double layer profile mean in this context?
so when you have a charged surface, right, you're going to have like an electric double layer established. So let's say if this is all negative, you're going to have a positive layer, then some negative layer, and then like
Yeah.
a diffuse layer. So you have a certain characteristic length, right? That's determined by what potential you're applying, the concentration. So if you end up putting a layer right before the electrical double layer reaches the bulk concentration of stuff, then that means that the concentration over here is restricted, right? Like it's not reaching bulk concentration. So it's always going to be, let's say, your reaction uses up certain counter ions, right? Then there's going to be an increased driving force for other counter ions to migrate into this space. And it's not just a diffusion, it's a migration. That's an interesting, like, extra driving force that comes.
But it's just the fact that you have a potential over a very small distance.
Yes.
Okay, yeah.
Yes, for sure, for sure.
So these are like 2 electrodes.
This is the electrode. This is like kind of
Capacitor.
yeah,
Okay.
yeah. But you're not charging this up. When you're applying a bias, you're only applying to one of them.
Yeah, but you still get probably like surface charges on the other plate or whatever, right? You have to have something.
I guess that depends on like,
On the material you make it up. But like, okay, sure. What is the second plate made? Are they both made out of the same material? Or?
it doesn't have to be. Or
Okay.
more often than not, it's not.
Okay.
Yeah.
So like one is a metal, presumably.
Yes.
And then the other one is like a
Yeah, so
thing, like.
yeah, so for example, the system that I'm going to be talking about is a metal ligand confined system. So I have metal at the bottom. So this is silver 111, for example. And then I have a tetradecyl phosphonic acid on the top. So this is like a 14 carbon chain with like a phosphonic acid head group at the very end. So think like really long with like 3 things pointed at the bottom.
This is periodic.
This is all periodic. So you can see how like these things are stacked up like one after another, and those long carbon chains are going to like have van der Waals interaction with its neighbor, right? So think soap missiles around like that kind of a structure.
Okay.
Yeah. That's it. Okay, so let's move on to, yes.
I'm just like having a hard time understanding under experimental like setup, like experimentally wise, like how are you restricting these molecules, the tetra, the ligand, how are you restricting them to make this one layer to confine the reaction to happen in this area?
That I am going to be answering in a bit. Yeah.
Okay.
But if you feel like your question isn't answered, feel free to like, interrupt me and we can discuss it. All right. So this is the system that I'm going to be considering. It's a silver at the bottom, the organic ligand on top, and it's called silver noli or silver nanoparticle, ordered ligand, interlayer structure, right? And the pocket between these two is the pocket where we hypothesize the CO₂ reduction reaction to be happening. So this is the structure that's what I'm going to be talking about. So my presentation is 3 bits. There's going to be 2 projects under structure and 1 on function. So under structure, I'm going to basically talk about how it is created, which is just her question essentially. The creation process is not trivial, as you can probably imagine. And then once I cover how it is created, I'm going to push forward and see how we can create it more energy efficiently, right? And then once we have delved so deeply into the structure, we then move on to function. And of course, we know that, the nanoconfined electrocatalysts enhances catalysis. Of course, we know that. We have talked about it. But in this particular project, I'm going to consider one specific reaction, which is the CO₂RR, and I'm going to consider one specific effect of nanoconfinement and see its impact. All right, so let's push forward. So the story began when an experimental group reached out to us and talked about their system. So they had silver nanoparticles, they had this tetradecyl acid, and what they found was that they kept getting really high CO selectivity and really high reaction rates only when they biased the system to like really large negative potentials. So what was going on? Like, this is the context in which reaction is happening. So this is where all of us, hypothesize that what's probably happening is that at really large negative potentials, this kind of a structure forms, our hypothesis, right? And the only reason why there is enhanced catalysis is because it's a nanoconfined electrocatalyst, right? Here. All right. So in order to prove that, we decided to use a computational setup, which basically involves the silver 111 surface that I talked about. And the ligand, instead of a C14 chain, I have like cut it down to C4 now because, it doesn't really make an impact in the overall trends we saw. So C4, it has been.
So you said it was nanoparticles though, right? So with there's not curvature here in the.
No, these are like 5.8 angstrom length scale.
Okay.
So
okay, so
it's a little too small.
It's flat, but these are essentially large enough, but they're deposited on a surface or something with an electrode.
Yeah. I think we are trying to like capture one part of the phenomena that's going on. So you have the ligand on top, which is actually supposed to be C14, but we have shortened it to C4. And yeah.
For the structure here, don't you see that you will have like periodic interactions between the alphabets since they are huge and the surface is really tiny?
Yes, that is the point. One of the points that makes it stable.
Okay, okay.
Yeah, you do need interactions between the ligand, and I will touch upon it in a bit. But yeah, the system is so small, which is basically one ligand in a 2x2 supercell, because experimentalists found that this is the ligand density in which the entire system is stable. So luckily for us, it ended up like being a perfect fit of like 1 in 30 angstrom square, which ended up being one ligand in a 2x2 supercell. So we have created this system, and our point is to use DFT calculations to get the energies of all of the configurations that's possible. So what we want to show out of this project is that nano-confined pocket only forms at really large negative potentials, right? That's our hypothesis. So to show that, we first consider all of the possible structures that's possible in the system. So you have a tetra or like a PO3 2 minus head group, 3 oxygens. So these 3 oxygens can all bond onto the surface and create a tridentate structure. Perhaps it's not 3, maybe it's just 2, in which case you have the bidentate structure, so like 2 oxygens over here. Perhaps it's just 1, in which it's monodentate. And then finally, no oxygen is bonded, and it would be the non-dentate structure. Now you can see, I hope right now, is that the non-dentate structure is the one we are interested in, because this is a structure in which the ligand is completely detached from the surface and creates this pocket. So non-dentate is the nano-confined structure of all of the 4 structures that are possible, right? What we interestingly found is that to create these 3 last structures, I needed to use water molecules to prevent the ligand from collapsing back onto the surface. So as soon as I like tilted the ligand, I had to put a little bit of a water molecule over there to prevent like collapse, which kind of goes in line with our experimental findings, which is that tridentate is only stable under vacuum conditions. So as soon as you have some amount of water, it's bidentate. So water also is a component, and if there is a pocket forming, it's going to trickle in, right? So this forms the basis of our hypothesis about why non-dentate or nano-confined might be forming only at really large negative potentials. So at really low potentials, you have the tridentate, especially if you don't have water, right? Now, as soon as you start putting a little bit of negative bias, then you're going to create the bidentate structure, because your oxygen in the ligand is negative and it's going to be repelled away from the negatively charged surface. So it's going to repel and it's going to tilt a little bit away and then create a little bit of a pocket over here where some water, because water is always present, is going to trickle in. The more negative potential that you apply onto the system, the more the thing is going to detach, tilt away, and the more water would be trickling in, until finally you apply so much negative bias that it's completely repelled away and then completely detaches. And then you can see that the pocket that will form between the detached ligand and the surface on the bottom is going to be filled with water. So this is the hypothesis that goes behind, creating the non-dentate or the nano-confined structure, and it's a combination of repulsion, tilting, and water interpolation. So that's our hypothesis. To really show that this is the case, we ended up plotting like an energy map as a function of potential. So I got the energies of all of these structures. I assume that the energies are linearly proportional to the applied potential. And then I ended up finding out the places where these particular structures are stable as a function of potential. So what I found was that at more positive potentials, it's tridentate. As soon as you start like making it more and more negative, it moves from tridentate to bidentate to monodentate, and then finally to non-dentate. So that's what we had hypothesized before, and that's what we confirmed with our computational methodology as well. So that's kind of it so far for project 1, but I want to draw your attention to the fact, to the subtle fact that sure, we have mapped this evolution, but we have also gauged what is the transition potential from tridentate to bidentate, bidentate to monodentate, and monodentate to non-dentate, right? Like this value, we know, we can calculate. That transition potential value, especially between like monodentate and the non-dentate, that value is a descriptor for determining how easy it is to create the non-dentate or the nano-confined structure. Because if this value is very negative, then that means you're applying so much more energy to create it. So if you want to create this in a more energy efficient manner, you're going to clearly see that you need to push this potential to the right and make it more energy efficient. So that's going to form the thesis of our second project. Can we create it more efficiently?
Sorry, I have to go.
Yeah, of course, of course. Thank you for listening so far.
Thank you.
Yeah, you can.
Thank you.
She's working on catalysis.
Awesome.
Yeah, and then they have someone's working, Ping is working.
Ping is working.
Yeah, with
She probably will look at your recording.
yeah,
Awesome.
we have someone working on nanoconfinement.
Awesome. I'm glad. Let's see, where was I? Okay. So our objective so far has been to try to create it more efficiently, and which means that we need to now start changing aspects of our component, right? Like easiest way to change something about the system, change something about the component. So there are multiple components here. You can see there's the ligand, there's the interface, and then there's the surface. And I am gonna be trying to modify one of each. So in the ligand case, I have decided to target the length and the density. So I'm going to change both of these parameters and see whether I can push the transition potential this way, right? Because that's the way I desire. I'm going to add an interfacial proton, see which way the transition potential moves, and then I'm going to introduce a series of surface defects to see where it moves. So that is my set of experiments that I'm doing. Let's first consider the ligand situation. So currently in my previous project so far, I have looked at one ligand in a 2x2 supercell, and I have looked at a C4 chain. So I've looked at like this system. Now I've expanded it to include like 5 other systems. So I've like changed the ligand density from 2x2 to 2x4. And I've changed the carbon chain length going from 4 to 2 and 4 to 6. So I have like 6 systems in total. And I've plotted specifically the transition potentials because that's what I'm interested in, right? So you can see if you compare 2x2 to 2x4, the 2x2, the transition potentials are a little more positive compared to the 2x4. So in terms of density, you want it to be more dense. Within the 2x2, it is when you move from C2 to C6, the transition potential also moves right the direction you desire, which means the more dense, the more long, the better in terms of creating the non-dented or the nanoconfined structure. Why? 2 words, agglomeration effects, right? So detaching the ligand takes considerable amount of energy, right? But let's say if you had other carbon chains around which are also detached, which can agglomerate with you, then it's going to be a lot more stabilized. So the more the carbon, the better for agglomeration. The more dense it is, the better for agglomeration. So that essentially dictates how ligand density and length affects the pocket that forms.
Did you check that the the bands of the silver by itself are stable with respect to increasing the supercell?
Sorry, can you repeat your question?
I'm saying like the band structure of the silver.
No, I don't think I looked at the electronic effects as much. It was more structural. Do you have a like specific something you wanted to?
No, just like if you do get different properties of the bulk silver when you. So I'm wondering, like, I get you're focusing on the interaction between the things, but it could also be that you're changing the electrons in the silver too, right?
I see.
But it's fine. I buy it that it's probably mostly the confinement.
Yeah.
The agglomeration.
Yeah, but I definitely can talk about it further. Maybe there is some couple of experiments that I can like isolate the effect, but sure. Okay, so this is the ligand effect so far. Let's push on to the surface. So among the surface defects that I have considered, I have considered like 3 classes. So the first one is obviously pristine silver, which we know and love. And then I have tried doping with copper. I have tried doping with gold. And I have tried removing silver atoms to create silver vacancy. So like 3 overall defect classes. And then even within the defect, I am removing 1 or 2 or 3 or 4 to like really change the doping or like the defect concentration and see its impact. So for all of these 3 defect classes, I plotted the transition potential, once again, what we're interested in. The overall takeaway so far is that with increasing defect order, copper and silver vacancies, the transition potential shifts left, not the direction we want. Only in gold does it shift right with increasing defect order. So what's going on, right? Like there's a trend that is observed, and I wanted to dig deeper into the trend as to what's going on. So I plotted the relative energies of copper, silver, and gold with defect order 4, where all of the top atoms are replaced by the heteroatom, plotted the energy. So you see clearly, in more precision, the copper less than silver less than gold trend in the overall system. I wanted to dig deeper and see where it is coming out from. Like, what is this trend about? So what I did was, of the entire total energy, I isolated the ligand surface interaction component, just that energy alone, and plotted that. Also follows the copper less than silver less than gold trend. Once again, I digged a little more deeper. I removed the other atoms that is not bonded onto the ligand and just considered an add atom and also plotted that energy. So just the interaction energy also follows the copper less than silver less than gold trend. So whatever is happening in the overall system is also happening at like the very fundamental interactions that's going on, right? So I decided to like go all the way to the extreme, all the way to like maybe single atoms and see whether the trend is replicated. So at the very extreme exists electronegativity, right? Because that essentially tells you what's like the possibility of bonding or electron transfer between two things. And I plotted that also on this side, right? So here there is an opposite trend. So clearly some of these are correlated, and the missing piece in this puzzle is the electron transfer. So it's like very clear immediately as soon as like, you get the charge transfer. So what we get so far is that the highest charge transfer happens in copper and the lowest happens in gold. So the highest charge transfer with copper add atom means that the bond is so much more stronger, which means you need to put a lot more energy to break the ligand away from the surface and form non-dented. In gold, it is much easier to break that bond and form that non-dented structure. So that ends up encapsulating our surface defects phenomena. Gold doping is better because it decreases the charge transfer. All right, then let's push on to interfacial protons. So here I started with initial structures with the proton in the FCC site and then let things relax. I only got a stable bidented and a non-dented structure. My monodented structure ended up becoming non-dented. My tridented became bidented, yada, yada, yada. Long story short, just my bidented and non-dented were stable. So I just plotted the bidented to non-dented transition potentials, which is different from what we've seen so far, but still gives us cool insights. So I plotted with the heteroatoms. Again, you can see the copper less than silver, less than gold trend being maintained. But what I want to draw your attention to is that these transition potentials, these values are way more positive, which means it has driven the transition potential all the way to the positive side, which means it is so much more easier to detach the ligand when you have protons present. Why? I think it's pretty obvious when you look at the structure. A detached ligand is just more stabilized when you have protons floating around to bond with it and stabilize it, right? So, summary so far, we wanted to move our transition potential to the right. We decided to do that by targeting the components in the system and changing aspects of it. And what we found so far is that ligand length and density helps, presence of interfacial proton helps, and then increasing gold opens or adding anything that decreases the charge transfer also helps in forming this non-dented or nanoconfined structure at lower potentials and also helping it be stable for longer ranges. Questions so far before we move ahead? Okay. So far, we have looked at all of the structural aspects. Let's now move on to function. So why does it enhance reaction rate? I mean, we have looked at nanoconfined electrocatalysts for enhancing catalysis, sure. Now let's look at one specific reaction that occurs in the system, which is the carbon dioxide reduction reaction. From a computational hydrogen electrode perspective, the CO2 reduction reaction is made up of these 4 steps. You have CO2 gas getting absorbed, forming the COOH intermediate, which becomes an absorbed CO, and then which desorbs to form like the CO gas. Of these 4 steps, the researchers have indicated that the second one is rate determining because it is the slowest step, right? So from a reaction energy landscape, it basically means that it takes the most energy to go from CO2 to the COOH intermediate, right? My hypothesis for this specific project is that if I'm able to stabilize COOH, chances are I'm stabilizing the transition state also involved and increasing the overall reaction rate. So what I'm going to try to show to you is that with confinement, COOH is stabilized. So the system design that I'm using for this project obviously has to have our pristine silver to like compare everything to, right? And then on the other side, I have the system that I'm interested in, which is silver anole with like the ligand, which is the confining part. And then in the middle, just to keep things a little interesting, I have decided to confine with another silver. So what I'm trying to get from this particular system design is the effect of confinement compared to no confinement, but also what is the effect of the confining species? Does it matter if you have an organic ligand or just a silver? Like, does it matter whether it's dipole interactions and van der Waals interactions? Does it matter what's the distance? You know, all of those other parameters.
So all the simulation so far is purely DFT.
Mhm. Yep. It's been pretty like powerful so far, but I'm super interested to move towards AIMD next. But yeah, so far DFT is surprised, which has been interesting. So my hypothesis is that on the extreme left, I'm going to have the lowest COOH stabilization because it's only bonded to one surface. And on the right, it's going to be the highest COOH stabilization because, of course, confinement exists, but dipole interactions are an order of magnitude stronger than van der Waals interactions, right? So the bonding is common to all of the 3 systems, and dipole interactions rule over van der Waals and no interactions. So that's the trend that I'm expecting. So let's see if that is a trend I do observe in actuality. So this is the reaction energy.
Would you consider that Ag to oxygen, the van der Waals at this distance, right? Is like
It's around like 6 angstrom, though this ends up being around like 2 to 3 angstrom, which is like around perfect.
it's a little short for like van der Waals, I would say, right? 'Cause-
There was, I think, so if you keep this as 5, right, then it starts pushing into the repulsive regime.
yeah,
Yeah, for sure.
Also, you have like it's almost a bonding interaction of like 2 to 3 angstrom. But yeah, okay, it's fine. I get what you're saying.
Yeah, I mean, we are pushing it, but to be fair, this is also the place where like van der Waals interactions play a more dominant role, right? So you could argue that, you know, it's an interesting and important thing to be considered. All right, so let's see if the hypothesis that I had carries out in the computations as well. So I have plotted the reaction energy landscape, you know, going all the way from CO2 to COS for pristine silver. And what I have so far, you know, is that, of course, CO going from this to this is like the rate determining step as we, you know and have seen. Now let's move on to a double silver. This is introducing confinement, but with van der Waals interactions. And I've considered 2 lengths. I've considered 5 angstrom and then a 6 angstrom and like plotted that energies as well.
Is this another layer? Is this periodic boundary conditions?
Yes.
This PBC, like 3-dimensional.
Yeah.
Okay.
So there is vacuum on top, of course, to prevent like
Yeah.
the image interaction, but like this is all periodic.
Okay. Oh, okay. So it's not. Okay.
It's not a sandwich structure.
Yeah. Okay.
It's not, yeah, no. Yeah, that makes me hungry a little bit, but okay. It's like, yeah, so I got those energies and into my landscape. And then finally, oh, sorry, you can see that it decreases. So any confinement, even a van der Waals one will do, sort of. And then finally, I push on to the system that we're interested in, which is silver noli. And you can see that it's an even more of an, stabilization for COOH. And that's because dipole interactions are so much more stronger than van der Waals interactions, right? So, yeah, I mean, that's what we've seen. But hold on. Enhancement in CO₂ reduction rate means that all of the competing reactions must be halted. The HER pathway is a competing reaction at ranges where CO₂ reduction also happens, right? Now, nanoconfinement can also enhance HER. So, I mean, if both of them get enhanced, then how are how is CO₂ getting enhanced more? Well, for this to happen, we need to plot the hydrogen evolution reaction as well, and somehow show that even if, which I'll show right now, which I use to show that even though confinement makes the hydrogen, absorbed hydrogen, which is what depicts the rate determining step in the HER, even though that gets stabilized and the overall reaction gets enhanced, the enhancement is, or like the stabilization is so much more lower compared to like CO₂ reduction reaction. So even though both of these reactions are accelerated, the CO₂ reduction reaction is so much more accelerated compared to HER that this ceases to be as much of a threat or a competing reaction anymore. So
This is the change, with the transition state or just the intermediate?
it's an intermediate. So I am definitely assuming certain aspects to be true about the transition state based on the intermediate for sure. Yes. Yeah, but that's because I think I wanted to focus on the intermediate stabilization aspect of it before I moved on to transition states.
No, I mean, it's just interesting to see it, like your scale is off, but it's actually a similar, probably barrier in total, right? Between,
Yes, I'm making a few assumptions for sure. Yeah. All right. So that kind of brings me all the way to the end of my presentation. So I've talked to you about electrocatalysis, about nanoconfined electrocatalysis, and then I moved on to the specific system of interest, which is silver noli. I talked to you about the structure of it, how it is created, the hypothesis that goes behind it, which is that you need to apply negative potentials to detach the ligand and to create that pocket, right? And it's not trivial for sure. And then we pushed on to trying to, look at ways of creating it at not so negative potentials, right? And we saw that some aspects of the environment can play a really critical role in stabilizing and forming it at lower potentials. And after looking at the structural aspects, we then pushed on to function and looked at one specific reaction mechanism, one specific reaction, or rather two, honestly, like CO₂ and HER. And we showed that COOH, or the rate determining intermediate, is stabilized in the confinement, which I am assuming means that the transition state is also stabilized, which is not, too far of a jump, and that any confinement would do, but a confinement that introduces stronger interactions would definitely be the most impactful. And then finally, I also want to say that even though nanoconfinement feels small and confining, it definitely opens up a lot of opportunities. And even though I have, and you can see that I've only considered one specific reaction and one specific nanoconfinement effect so far, and it's already been pretty insightful. You can imagine how much more insights we can get if we look at the other nanoconfinement effects and model to isolate and quantify the effects on like specific systems, right? So I think that's the direction in which like some of us has been trying to work towards. With that, I would like to thank my supervisors, Jen and Ethan, and their group. This is us going axe throwing, just to like let down some steam. And with that, I would like to open it up for questions. And thank you all for listening, of course.